The focus of this video is to illustrate an example of aggregate planning problem. So assume that the coffee shops at RPI campus purchase their pumpkin spice flavored ground coffee from a local producer. So this local producer has a limited number of workers. Therefore, the production capacity is determined by the workforce size. Since pumpkin spice coffee is popular only for certain time of the year, so like fall, winter, pumpkin spice coffee is popular, but in spring or summer it's not that common. So there exists a seasonality in the demand for pumpkin spice coffee. So the owners of the coffee shops will not be very happy if they cannot receive enough pumpkin spice coffee during peak seasons, because in this case the students will not be able to find pumpkin spice coffee on campus, so they are not gonna be happy either, and this is not good. So the local producer doesn't want this to be the case, and they need to plan against this seasonality. So what can the local coffee producer do in this case? They can hire workers in peak seasons. They can produce more than needed in slow seasons, which means they are building inventory here. Or they can subcontract productions to another company. Basically say, okay, we cannot produce the required amount, so we are going to make an agreement with another company that can produce this remaining amount. And another option is backlog the demand. So make customers wait to get their orders. So these are some of the options. So this issue that the local producer is having can be handled by aggregate planning. This planning is used to make decisions about production, outsourcing, inventory, and backlogs at an aggregate level. So this is good because it provides some flexibility. Like you have some uncertainty in your demand, so there are fluctuations, and by using aggregate planning you provide some flexibility in your planning. So in general, the input to an aggregate planning is aggregate demand forecast by using the past data. So your demand in this case is a parameter, so you forecast your data demand based on the past data and feed it into your aggregate planning problem. Production costs, you have labor costs, it can be regular time or overtime, subcontracting costs, cost of changing capacity, you may want to hire workers or lay off, you may want to add or machine capacities, you have labor or machine hours required per unit, inventory holding cost, stock out or backlog cost, and some constraints like overtime. You may have a restriction on overtime, layoffs, capital available, stockouts, backlogs, and so on. And by using this input, you can determine the following. So production quantity from regular time, overtime and subcontracted time. You may determine how much inventory to have, backlog and stockout quantities, workforce hired and laid off, and how much to increase or decrease your machine capacity. So in general, when you model a mathematical problem, if you know something in advance, stuff like this, those are your parameters. If you don't know the things in advance and you are going to know their values after you solve your problem, then those are your decision variables. So the statements on the left are basically your parameters, and these on the right are basically your decision variables. So this is going to give you an idea about what we are going to do with this aggregate planning problem. So if we move on to our problem, so we have some data and let's talk about what we have. So the local producer wants to handle this issue because it's a serious matter, and they ask the industrial and systems engineering students to use aggregate planning to manage this situation. So the students used the past data and found the forecasted demand for 8 periods. So this is our demand, which is a parameter, and this is going to be an important parameter of our aggregate planning problem. So it is given in table 1. We have our forecasted demand in units, and there are some other values that we know in advance. So the local producer has a starting inventory of 40 units. So when we start this planning horizon, we already have 40 units of ground coffee. You may say 40 boxes, packages, whatever that is. So 40 units we have. And initial workforce size is 50 workers. So we have 50 workers, say. And there are 20 working days in each period. So this period might be a month. So that there are 5 days in each week and 20 days in a month and so on. And each worker works for 8 hours a day during regular time. Production of each unit requires 2 hours of labor, and workers are paid $12 per hour during regular time and $16 per hour during overtime. And workers cannot work more than 10 hours during overtime. Cost of hiring and training a new worker is $750 per worker. Cost of layoff is $1,200 per worker. Inventory cost is $10 per unit per period. Stock out backlog $14 per unit per period. Subcontracting cost is $100. We don't have any limits on backlogging, subcontracting, and inventory holding, so you can backlog or subcontract as much as you want. You can hold as many inventory as you want. The local producer aims to have at least 30 units of inventory at the end of the planning horizon. And the last restriction here is no stock out at the end of the planning horizon. So we don't want to have any stock outs. So this is basically the story of what we have, the local producers situation. They have these cost values, they have these other parameters, they have these constraints. So our goal is to determine the best aggregated plan that will minimize the cost. You can also think this as maximizing the profit. They are kind of equivalent here, or maximize the revenue, because you need to meet all of the demand and there is no variation in the demand. So demand isn't fixed and how much you make per unit is fixed. Therefore, saying that we want to maximize the profit is basically equivalent to minimizing the cost in this case, since your revenue is fixed over the planning horizon. So if we talk about the mathematical model, first we have a set. So our set is the number of periods in the planning horizon. So these is indexed on T 1 to 8 in this case, so 1 to 8. Parameters. Our parameter is demand. So dt is the number of units demanded in time period T, and T is from 1 to 8. Decision variable. So what we want to determine at the end, we want to determine workforce size for period T. So for each period, we want to know how many workers we have. HT, number of employees hired at the beginning of period T. LT, number of employees laid off at the beginning of period T. PT, how much to produce in period T. IT, inventory level at the end of period T. ST, number of units stocked out at the end of period T. CT, number of units subcontracted for period T. And finally, OT is the number of overtime hours worked in period T. So now let's formulate the objective function. The objective components are regular time labor, overtime labor, cost of hiring, cost of layoffs, inventory holding cost, stock out, and subcontracting costs. So the first component is regular time labor. So how much do we pay for the labor in regular time hours? So how much do we pay per hour? So we have $12 per hour. So that is $12 per hour. And how many hours a day do we have? 8 hours. 8 hours per day. And how many days in one period? We have 20 days. per period. So this multiplication gives us 20 per period. So this means per worker we have 1920 per period that we have to pay. So in our objective, this is going to show up as 1920 WT. So for each worker, we are going to pay 1920, and this is going to be the same for each period. Therefore, we have to sum it over T. I'm not going to write this explicitly because that's gonna be very simple, same idea. So the open form of this is basically 1920 times W1 plus 1920 times W2 plus 1920 times W3 and so on. So summation notation is an easy way for here. So overtime labor. So how much do we pay for overtime hours? So we have, if you look at this data, overtime cost is $16 per hour. So summation for each period, we are going to pay 16 OT. So OT is the amount of overtime hours worked, and for each hour we are going to pay $16. Therefore, this summation is going to give me total money paid for overtime labor plus cost of hiring. How much do we pay when we hire and train a worker? That is given here. The cost of hiring is $750 per worker. Therefore, we are going to sum 750 HT. HT represents how many workers we hire and train, plus how many workers that are laid off. For each worker that is laid off, we have to pay $1,200. Therefore, LT, T is over 1 to 8. So this basically says for each employee that is laid off in period T, we are going to have to pay $1,200. And we are going to sum all of these 1,200 times LTs over T because we have 8 T values. And the next component is inventory. So how much inventory we hold and how much do we pay? So summation over T again, and inventory cost per unit. Inventory holding cost is $10 per unit per period. So 10 times IT. So IT is the inventory level in period T at the end of period T. And therefore, for each unit of inventory, we are going to pay $10, and this is for only one period. We have 8 periods, and we are going to sum all of them up. Next, stock out. Stock out cost is $14 per unit per period. Summation T from 1 to 8, 14. Stock out is represented by ST, and the last one is T from 1 to 8. Subcontracting. How much do we pay for subcontracting? $100 per unit. Subcontracting is CT. So therefore we have our objective function formulated, and we have all of these cost components available in this function. So next step is the constraint set. How many constraints we have and what are these restrictions? So the first constraints on the left, you see my constraint sets. The first constraint is to compute the workforce. So for each period, I need to compute how many workers we have available. That is going to be computed by WT equals WT minus 1 plus HT minus LT for all T values. So what this means is the number of workers in period T is equal to the number of workers from previous period and the number of workers I hired in this period minus number of employees we laid off in this period. So for period 1, for example, you can write it down as W1 is equal to W0 plus H1 minus L1. And this makes sense because we want to compute how many available workers we have, and it is calculated by the number of workers from previous period, number of hired workers, number of laid off workers. So this is that, and also as I listed as 1.1 W0. So how many workers we have at the beginning? W0 is 50. If we go back to our previous slide, the initial workforce size is 50 workers. Okay. So the first constraint is set. The second constraint is capacity. So the amount produced cannot exceed the available capacity. So I need to compute my available capacity. So I'm going to write this down explicitly. So for period 1, amount of production is P1. That must be less than or equal to my production capacity. So for regular time capacity, I have 8 hours per day, right? And how many days I have in a period? 20 days per period. This is 160 hours per period. Therefore, how much labor hours required per unit? So if we go back to our data, in this statement, production of each unit requires 2 hours of labors. So I have 160 hours and one unit requires 2 hours of labor. Therefore, 160 divided by 2, 80 is the production that we get from one worker. So one worker can produce 80 units. So therefore I need to multiply 80 times W1. So number of workers available in period 1 times 80, because each worker can produce 80 units plus my overtime capacity. So overtime capacity is a little tricky. So we have total number of overtime hours. So O1 is my overtime hours. How many hours do I need to produce one unit? 2 hours. So we need to divide this by 2. For example, say we work 6 hours overtime and I need 2 hours to produce 1 unit. So divided by 2, I can produce 3 units. Therefore, this value is basically corresponding to this 3. So this O1 divided by 2 tells me how many units I produce in overtime. So that is my overtime capacity, whereas this 80 times W1 is my regular time capacity. So this is going to be the same idea for all periods, and I'm going to generalize it and say PT less than or equal to 80 WT plus OT divided by 2 for all T values. Constraint 3, inventory balance. So this is going to sound a little complicated, but it is really not that complicated. So inventory at the end of last period plus production amount in the current period plus amount of units subcontracted in the current period must be equal to demand for current period, number of units stocked out in the previous period, and inventory at the end of the current period minus number of units stocked out in the current period. So basically what we are doing is, in our current period, we are considering how much we have from the previous period. And then we also look at the future, how much we are going to consume in this period. Like demand is going to be met, there is going to be some stock out, and we are going to meet the stock out from previous period and so on. So we need to balance the beginning inventory and the ending inventory. This is what we are doing in this constraint. So in general, for all t values. it minus 1 plus pt plus ct equals dt st minus 1 it minus st for all t values. And for t equals 1, this is going to be I0, right? So my I0 value is my initial inventory, which is, I need to go back to my data, which is 40 units. And my S here is going to be S0. My initial stock out value is 0. My ending inventory must be at least 30 units. If we go back to our problem statement, sorry, it says at least 30 units of inventory. I8 is greater than or equal to 30, and there is no stock out allowed in the last period. So these are the additional constraints. So the left-hand side here tells me what we have from at the beginning of the period, and the right-hand side tells me what I am doing in this period and what I'm going to leave for the next period. So this amount must be balanced. It's what this constraint basically says. Fourth constraint is overtime limit. Again, I'm going to write it for all t values. So overtime hours worked in period t must be less than or equal to 10 times WT. The restriction says workers cannot work more than 10 hours of overtime in each period. So 10 times number of workers available must be greater than or equal to overtime hours in that period. And this is for all t values. The fifth constraint is decision variables. So all of our decision variables basically are greater than or equal to 0. HT, LT, PT, IT, ST, CT, OT, greater than or equal to 0 for all t values. So there is this 6 here, which is not a valid constraint in our problem because we don't have any restrictions on backlogging, subcontracting, inventory holding, but it might be a constraint for another company or another problem. So you may need to pay attention to those restrictions as well. But in our problem, it's not a constraint.